In this video, we're going to talk about the nature of electromagnetic waves. Mostly, I admit, we're going to mostly focus on light, which is only a certain range of frequencies of electromagnetic waves. So we'll often talk about light because we're most familiar with light, but all these properties have to do with all electromagnetic waves. First things you need to know about electromagnetic waves are a bunch of random facts. Now these facts could pop up anywhere on a test, and you do need to know these. So all of these is worth taking the time to write all these facts down. First of all, the frequency of an electromagnetic wave affects, especially light waves, affects what color you see. The amplitude affects how bright that light is. And all electromagnetic waves travel at the speed of light, which is 3.00 times 10 to the 8th meters per second. Now that number pops up a lot and is really important to remember. And this is the speed of all light waves and all electromagnetic waves in a vacuum. A lot of people forget when we're doing a problem when we say, there's a radio wave, and they'll think, well, I don't know how fast it's going. But remember, it's an electromagnetic wave just like light, and therefore travels the speed of light. Radio waves, gamma rays, X-rays, infrared, all those go at the speed of light. Those different names that I was naming for those are different bands of electromagnetic waves. There are 7 main electromagnetic bands, and you need to be able to know all 7. You need to memorize the names of all 7, and you need to be able to list them in order of frequency and in order of wavelength. Each band is separated by certain frequencies. So light, for example, I don't know the exact band off the top of my head or the exact frequencies, but light is any electromagnetic wave between the frequency of A and B, whatever those 2 frequencies are. And those are the frequencies that our eye can actually absorb and detect. Any other frequencies our eyes cannot absorb and detect, and therefore it is not light. But different bands are useful for different applications, and so that's why we have different names for them. But you need to know all 7 of the major bands, and then you should be able to list the names in order of highest to lowest in frequency, or highest to lowest in terms of how long their waves are. You also need to memorize all 6 colors, which are like more bands within light itself. So you can break light into smaller bands, which we define as different colors. And you need to be able to list those in order of frequency and wavelength as well. These things you'll have to look up and on WebAssign or in a reading or on a website of some sort, and write these down in your notes. Electromagnetic waves, you should also know that when they have a higher frequency, they also have more energy involved. You should also know that all electromagnetic waves are transverse and are made up of oscillating electric and magnetic field. And when the electric field oscillates, it is perpendicular to the magnetic field. So as the wave moves forward, the light beam goes forward, the electric field might be oscillating up and down, which is represented by this white part, but the magnetic field oscillates perpendicular to the electric field, so side to side. Both, though, are perpendicular to the direction the wave travels, and therefore light is a transverse wave. All right, so now that we got some of the just random facts down, let's talk about how you make an electromagnetic wave. A wave is made when you accelerate any kind of charged particle. For example, I could take a flashlight and I could turn on a flashlight, and what I'm doing is I'm accelerating electrons through a little filament, usually tungsten or something like that, and the electrons, as it goes through, will excite and heat up the molecules in the atoms in the tungsten, and they wiggle, and those electrons in the tungsten will vibrate, and as those electrons vibrate and accelerate, it disturbs the electric field and sends ripples through the electric field. Okay, so also you should know that you can also create electromagnetic waves by releasing energy in terms of electric energy or electrons dropping in energy as well. So if they, whether electrons or molecules or or the nucleus drops in energy levels, that energy can be spat out in the form of an electromagnetic wave. All right, so what are the different properties or phenomena that electromagnetic waves can perform? Well, as with all mechanical waves, electromagnetic waves can also reflect, transmit, refract, and diffract, and have superposition. The difference, though, is that with electromagnetic waves, they also have 3 additional phenomena. They also show the phenomena of dispersion, scattering, absorption, and emission. These 3 additional phenomena you need to know about, and you need to know how they work, and we'll talk about each one in detail. First, let's talk about dispersion. Dispersion is something we've all seen, and it is the phenomena that higher frequencies will, or ones with shorter wavelengths, will change direction more than ones with lower frequencies. So, for example, blue and purple and violet have a higher frequency than red. So when you shine white light into a prism and it transmits into a new medium, the light will refract as all waves will when they enter a new medium. The difference, though, is because with electromagnetic waves is that because blue has a higher frequency, it will actually change directions more, and it'll bend more. Red, having a lower frequency, will just change directions less. So while blue bends a lot and ends up here on the piece of paper, red ends up over here. Thus, it actually splits the different colors within the band of visible light. This is true with all the different bands of electromagnetic radiation. However, we can see it with light, and therefore we often use it and when we talk about it with light. Dispersion is the phenomena that explains how rainbows are made. Scattering is another phenomena that involves an interaction between molecules. When there are certain molecules in the atmosphere or in the air, and electromagnetic waves pass by these molecules, sometimes, depending on the molecules, the light will react with these molecules, and they'll just randomly be redirected into another direction, and it will only happen with certain molecules and certain wavelengths of light. You need to know some practical applications of where scattering occurs. In addition to knowing what scattering is, you need to know practical applications for scattering. These often pop up on the IB test. The most commonly known application of scattering is to explain why the sky is blue. This is a phenomenon known as Rayleigh scattering, which is a specific kind of scattering. Now, scattering, or why the sky is blue, I've seen that also pop up, that specific question pop up on the IB test, so it's worth going over. Okay, so let's talk about it. When, remember, scattering is when light is redirected randomly because it interacts with molecules, right? So sunlight will travel, and it is white when it leaves the sun, meaning all colors of the rainbow, all frequencies of light are sent from the sun towards the earth. So this white light, which is made up of all colors, as it passes through the atmosphere has molecules such that it just happens to like to scatter the color blue. And so all the lights pass right on by the atmosphere and are not affected, but blue in particular is the one that doesn't continue and is scattered in all directions. So while this person down here on Earth looks up at the sky at this location, they're going to see blue, because blue light is the one that comes to his eye from this location. If someone was over here and was looking up at the sky, they would also see blue. Blue is scattered in all directions. It's random, but it turns out to be all directions because of that randomness. Now, if we had no atmosphere, so in other words, if blue continued going straight, when a person would look up at the sky, they would see nothing. If you had, for example, someone was over here and had a laser and was shining the laser this way, you looked up, you would not be able to see the laser. you can only see something if the light goes to your eye, right? So if they shine the laser straight to your eye, well, then you'd see the laser and you'd be saying, ow, 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 right? Similarly, you can't see the light that passes above your head unless it's redirected and coming to your eye. This is why it's only blue that you see. Another phenomena that scattering also explains is why sunsets appear red. Now, when the sun sets and is low on the horizon, it passes through a thicker blanket of the atmosphere because of the curvature of the Earth. And so it'll end up scattering more of that blue light. Now, as more of the light is scattered, the blue light goes everywhere, including some towards your eye, but most of it is scattered everywhere else. So very little blue gets to your eye. Because of that, because of the lower frequency, or sorry, that's higher frequency, because the higher frequencies of light are scattered, the lower frequencies are predominantly the ones that actually continue through, those lower frequencies being more on the red colors. So the sky appears more red during a sunset because that light's coming more directly to your eyes. The last phenomena of electromagnetic radiation is that of absorption and emission. So hopefully you recall this from chemistry, but if you remember right, each atom is made up of a nucleus and electrons that, for lack of a better word, orbit the nucleus. Okay, and really they exist in an electron cloud right around that nucleus. And these electrons exist in certain energy states, and they can be found in certain energy levels that we often call shells. Okay, so absorption is when a hunk of electromagnetic radiation, or which we also call a photon, when a hunk of electromagnetic radiation comes along, and if it's the right amount of energy, I mean the perfect amount of energy, that electromagnetic radiation will just disappear. Okay, and instead what will happen is that energy will turn into bumping up an electron to a higher energy level. However, the energy has to be just perfect, the exact amount of energy that it requires to go from this energy level to the next higher up. Emission is the exact opposite. All electrons seek their lowest energy level possible, and so oftentimes if they ever get bumped up, they will eventually fall back down. And when they fall back down, it loses energy, and it gives off that energy in the form of electromagnetic radiation. So it'll spit off an electromagnetic wave. Okay, so here's an example of what that might look like, right? So here is a hunk of electromagnetic radiation, we also call a photon, okay? And it might come in, and if it's the perfect amount of energy, bumps it up, and then this will randomly fall down to a lower energy level, and when it does, it'll spit off that exact same wave because it has the exact same amount of energy. Now, one thing that you should know is, for example, like how fluorescent light bulbs work. A lot of houses have fluorescent light bulbs. Our school has fluorescent light bulbs. And what happens is there's a big electric potential or a large amount of voltage on both ends of that fluorescent light bulb tube. And what happens is there's a lot of energy there, and it excites all the gas molecules, all the electrons in that gas molecules. It excites them all up, and they all jump up to higher energy levels. But then they randomly fall down. Now, when they randomly fall down, it'll emit these photons out, and it'll go in any random direction, and you never know when it's going to occur. The problem with that is that when you're trying to create something like a light source, okay, and you want light, for example, for an interference pattern. Remember, one of the requirements are you need coherent light sources. But since it's random when it emits those waves, you can even emit the same frequency of wave every single time, an electromagnetic wave chunk with the exact same frequency and exact same amount of energy every single time. But because it's random, it's never going to be in sync with other photons or other chunks of electromagnetic radiation that'll be spit out. And so these photons, they will have random phase shifts, and they're definitely not coherent. Light that comes from fluorescent bulbs and light bulbs are definitely not coherent. So remember, in order to get an interference pattern, we need coherent light and preferably monochromatic, so one frequency. So how exactly do we get that? Well, we're going to talk about that, and the main way we get that is with a laser. Lasers are something that create monochromatic light, so a single frequency. That light is coherent and it's directional. So we now are going to learn about how lasers work in our next video.